Dr. Collins, you are welcome, and thank you very much for accepting the invitation to participate in this episode of the Café Geológico. Please, I ask you to say a first hello.
Hello, greetings, and thank you very much for this invitation. It's 2 months ago now when I was visiting Brazil for the Brazilian Academy of Sciences in Rio de Janeiro, and it was a great experience and a wonderful opportunity to visit Brazil. And it's nice to be visiting you again today, even if it's virtually. Thank you very much. I'm just getting this screen up so I can see it as well. So thank you all for this invitation to talk to you today on the topic of the Anthropocene. My perspective is during this presentation will be as chair of the Anthropocene Working Group, the official body established to investigate the potential of adding the Anthropocene to the formal geological timescale. However, it's clear that the implications of the term reach widely through the sciences and humanities. It's a new way of thinking about our overwhelming impact on the planet Earth. If we focus on the Quaternary period, which is the 2.6 million years in which continental ice sheets have extended over large areas of both poles, there are currently formally only 2 epochs. 99.5% of the time interval of the Quaternary period is taken up by the Pleistocene epoch, with repeated advances and retreats of ice sheets as climates varied cyclically. The latest of some 50 more temperate phases, known as interglacials, have been recognized as the Holocene epoch, commencing 11.7 thousand years ago. Broadly at the end of the last ice age, it is subdivided into 3 ages, with boundaries defined on the basis of more minor climatic events, such as the 8.2 and 4.2 thousand year ago events. The Holocene is only remarkable in the context that human civilizations, urban societies, and agriculture all developed at this time, but notably, human impact was not responsible for the climatic changes used to define the epoch and component stages. Humans responded to planetary change rather than being the cause of it. The Anthropocene, as a proposed new epoch of geological time, would be at some 70 years so far, by far the briefest geological time interval currently equivalent to the traditional understanding of the average human lifespan. Some would argue that such timescales are not geological, but in this presentation I will explain why we feel it should be formalized as a new geological time unit at epoch rank, and what it says about the nature of our impact on the planet. So in this presentation, I want to introduce, first of all, an understanding of what the term the Anthropocene means, then have a focus on the evidence for the mid-20th century onset, which we prefer within the Anthropocene Working Group, and then finally introduce the work in progress in finding a golden spike section that will be used to propose a definition. So the term originated from this gentleman, Paul Crutzen, who's a Nobel laureate atmospheric chemist. It was at an improvised suggestion at a conference in 2000, as he became increasingly frustrated about speakers referring to the present as the Holocene. Although he was considering the operation of the whole Earth system, not just the geosphere, Paul Crutzen's vision is seen clearly here in the first published usage in 2000 as a geological term, where he states, "It seems appropriate to assign the term Anthropocene to the present, in many ways human-dominated geological epoch, supplementing the Holocene, the warm period of the past 10 to 12 millennia." The heading of the article, Geology of Mankind, and similar terms such as Age of Humans, causes some confusion that some have attempted to promote as suggesting that the Anthropocene relates to all anthropogenic impacts on the planet, however small and distant in time, very much contrary to the original proposal. So Will Steffen, who is an Anthropocene Working Group member who sadly died earlier this year, was instrumental in developing the Great Acceleration concept, introduced in this paper published in 2007, subsequently updated in 2015. This provided evidence that soon after the end of the World War II, there was a phenomenal change to the planet. This great acceleration is expressed as marked upturns in socio-economic trends, including population, economic growth, energy use, urbanization, globalization, and agricultural development. These are then the drivers for changes to Earth system trends, such as increases in concentration of greenhouse gases in the atmosphere, resultant climate warming, changes to marine ecosystems, including ocean acidification, changes to the nitrogen and carbon cycles, and to biosphere degradation. These trends are evident as signals seen in the geological record and will be the focus of much of the next section of this talk. But firstly, let's look at a couple of examples of more significant socio-economic trends in detail. That's population and energy use. So a reality of the Anthropocene is that over recent decades, there's been basically more of us to make an impact on Earth's system. At the start of the Holocene, at the end of the last ice age, global population is estimated at about 2 million people. Over 11,000 years, that increased slowly until the onset of the Industrial Revolution, when it was about 800 million people. Population growth shows an inflection about 1950, since when the population has more than tripled from 2.5 billion to 8 billion. If we average that across the global land surface, it's gone up from about 1 person per 50 kilometers squared at the end of the last ice age to some 60 people per kilometer square now. But not only is it the vastly increased population, but also that every individual aspires to a much better quality of life, with increased consumption, development of globalized networks, and increased technology, ensuring that each individual has a much greater impact on the planet during the Anthropocene than they did during the Holocene. So a major driving force for many of the changes observed through the Anthropocene has been a significant upturn in world energy production in the 1950s, in particular with rapidly increased production of oil and natural gas, which parallels the increase in global population. So greater than 90% of all the coal, oil, and natural gas ever exploited have been burned since 1950. It's estimated that total energy use since 1950 is 1.6 times greater than all previous human history. And the 36 billion tons of carbon dioxide emitted in 2021 far exceeds natural emissions from all volcanoes on Earth, which yield about 200 million tons per year. This is a potent example of how we are significantly overriding natural processes. So next, I want to briefly introduce some of the many key signals for the Anthropocene, which can be subdivided into 5 categories. And these are listed here. So novel materials, so that's novel mineral-like compounds, concrete, fly ash, plastic, changed flux of sediments, so that includes fluvial systems and artificial deposits. Then there's geochemical signals, so that's changes to the carbon, nitrogen, and sulfur cycles, heavy metals, and domestications. Okay, so a useful summary of the key signals in this paper in Science, published in 2016 by members of the Anthropocene Working Group, and many of the figures used in this presentation are sourced from here. So I'll start by talking about those novel human-generated materials, which include greater than 200,000 artificial mineral-like compounds, which far exceeds the 5,000 naturally occurring minerals. These cumulative production figures for aluminium and concrete are great acceleration curves. In 1900, few people on this planet would ever have seen aluminium as a metal. But in the last 70 years, we've produced almost all of the 500 million tons of aluminium, which is the red curve seen here. And over the same duration, we have produced in excess of 500 billion tons of concrete, which is the blue curve. If spread across the entire planet, it would equate with 1 kilogram per square meter. Although first developed by Romans, volumetrically, the vast majority of concrete has been produced during the Anthropocene. Plastics in the form of celluloid, rayon, and bakelite were rare before 1945. When we produced this figure in 2016, annual production was 299 million tons. 4 years later, it had increased to 367 million tons per year, again displaying a typical great acceleration curve. The cumulative production since 1950 at greater than 9 billion tons is more than triple the carbon biomass of the entire animal kingdom. Only about 10% is recycled. Much goes to landfill, but microplastics are increasingly finding their way into the fluvial and ocean sediments as a global marker almost exclusively of Anthropocene age. Another novel material that is now found globally are known as spheroidal carbonaceous particles. These are only produced by the high temperature combustion of coal and fuel oil. A typical thermal power station emits about 25 trillion such particles in a day. They're small, about 50 micrometers in diameter, and with distinctive pitted morphology, as shown in this photograph. Work by Neil Rose, an Anthropocene Working Group member, in lake successions around the world, shows a common pattern with first appearance in the mid-1800s, typically earlier in the UK and Western Europe, and peaking in the 1970s to 1990s, later in the Southern Hemisphere, which is shown by the pale blue curve. but with a consistent upturn, a great acceleration curve around 1950, which appears a more consistent marker across the regions. This figure introduces the idea that some important markers of the Anthropocene onset may ultimately be emitted over a relatively short duration at the beginning of the Anthropocene, but that intervention measures introduced to limit pollution from these sources have the potential of eliminating this from the future geological accumulations. We need to consider also the scale that humans are refashioning the landscape and changing our understanding of our sedimentary systems. The land surface comprises about 27 trillion tons of human-modified materials from urban areas, crops, pastures, plantations, roads, rail, reservoirs, etc. If spread evenly across the continents, it would be 27 centimeters thick. The scale of change in various sediment loads just between 1950 and 2010 is astounding, as shown in this data from Anthropocene Working Group member Jai Savitsky. Soil erosion has tripled from 25 to 75 billion tons. But despite this increase, the amount of sediment transported from land to sea via rivers, wind, glaciers, etc. has actually decreased from 22.4 to 17.3 billion tons. And the amount of ocean sediment disturbed by trawler fishing has increased from 2.9 to 22 billion tons. When you include the other factors, some of which I'll be illustrating in the next slides, the sum of the change is greater than 300% increase in sediment load over only 60 years. A significant reason for the fall in sediment flux to the oceans is because humans have significantly perturbed river systems through construction of dams. There have been some 58,500 large dams constructed mainly since the 1940s at a rate of about 2 per day, including here in Brazil, the Itaipu Dam, one of the largest hydroelectric dams in the world by capacity, completed in 1984. There are an estimated impoundment of 3.2 trillion tons in all of the world's major reservoirs. This is equivalent to a 5-meter thick deposit covering all of Spain or California. This graph shows estimates for the production rates of anthropogenic deposits or artificial ground between 1925 and 2015. It includes minerals and mineral production and associated wastes, shown in pale blue, coal production and associated wastes during excavation in orange, cement and aggregate production in grey, offshore dredging in yellow, and civil engineering earthworks in dark blue. Again, we see a typical great acceleration curve with a 30-fold increase from 10.5 billion tons in 1950 to 316 billion tons in 2014. This is equivalent to 150 cubic kilometers of artificial ground generated in 1 year, which is about 43 tons per person per year for everyone on this planet. It is interesting to compare these figures with the sediment flux to the oceans, which I mentioned earlier, as showing a 23% fall from 22.4 billion tons to 17.3 billion tons over this interval. In 1950, sediment flux to the oceans by all natural processes was about twice the mass of human-generated sediment. But by 2014, this had flipped, such that human-generated deposits were 18 times more. I hope this enforces the argument that humans have become, during the Anthropocene, a major geological force. Next, we consider geochemical signals that can be used to identify the Anthropocene. There are many geochemical signals that show abrupt changes during the transition into the Anthropocene, a selection of which are shown here. They include carbon dioxide and sulfur concentrations, elevated particularly through fossil fuel burning and industrial pollution. Various metals, the product of mining and smelting, industrial pollution and fossil fuel burning. Persistent organic pollutants such as polychlorinated biphenyls, the product of industrial pollution. Various radioisotopes, the product of atmospheric nuclear testing. And nitrates, methane, and various pesticides linked to expansion of agriculture. It is not so much the first evidence or onset of human-generated signals that is significant, which as shown here can range over hundreds or thousands of years for different signals, but it is the sharp upturn or acceleration in signals that most consistently aligns around the middle of the 20th century. Note that for many of the signals, peak magnitudes occurred in the second half of the 20th century, and for some, recovery comes back in the 1950s levels has already been achieved. Let's look at some examples in more detail. This figure shows Antarctic ice core atmospheric carbon dioxide and methane variations over the last 20,000 years. The CO2 curve sits within the natural range over the last 800,000 years of some 170 to 300 parts per million, shown in yellow. However, current atmospheric values are 140 parts per million higher than pre-industrial levels, rising at a rate greater than 100 times faster than during the Pleistocene-Holocene transition. It is perhaps the most rapid, large rise of atmospheric carbon dioxide in all of geological history. CO2 levels haven't been so high since 3 million years ago, when temperatures were 2 to 3 degrees warmer and sea levels 10 to 20 meters higher. Methane concentrations have ranged from 350 to 800 parts per billion over the last 800,000 years. For methane, there is unprecedented rapid 1100 parts per billion increase, more than double typical Holocene levels. There has been a doubling of reactive nitrogen at the Earth's surface in the past century, partly in response to the increase in production of nitrogen fertilizers to some 90 million metric tons per year. That's the red Great Acceleration Curve. In large part a result of the introduction of synthetic fertilizers through the Haber-Bosch process in 1913. There's also some 35 million metric tons per year of nitrogen oxide emissions, principally from combustion engines. That's shown by the red dashed line. This has led in Greenland ice, shown by the blue curves, to a phase of nitrate concentration increase from 1950, culminating levels higher than those observed at any time in the Holocene. World coastal zones now receive about 100 million tons per year of anthropogenic sourced reactive nitrogen, leading to expansion of seasonal hypoxia and generation of dead zones, which are also seen in many lakes across the planet. Although not a fundamental driver of Earth system change, potentially the most widespread and globally synchronous geochemical event is the fallout associated with above-ground nuclear weapons testing. The black columns in this graph show the aggregate number of above-ground detonations that released radionuclides into the atmosphere. Early tests and the use of bombs at Hiroshima and Nagasaki in 1945, although terrifying in their destructiveness, were associated with only regional spread of nuclear fallout. It is not until 1952, with the introduction of high-yield thermonuclear devices, that's hydrogen bombs, that fallout was dispersed globally. These atmospheric detonations led to clear fallout signal, here illustrated with the green curve by radiocarbon and the blue curve by isotopes of plutonium. Plutonium isotopes are rare in nature, and their appearance in the geological record is almost instantaneous, which has led to the proposal that the upturn of the signal following the first hydrogen bomb test, the Ivy Mike test on the 1st of November 1952, shown in this photograph, is the most suitable primary marker for the start of the Anthropocene. They also show a clear double peak with a dip associated with a short moratorium in testing in 1959 and 1960, and decrease rapidly following the 1963 Limited Test Ban Treaty. The signal may have been generated widely for little more than a decade and provides a precise delineation of the base of the Anthropocene. So global warming is seen as probably the most significant planetary change during the Anthropocene, but its effects are not readily evident at the start of the epoch. The upper figure shows a greater than 3.5 degree temperature increase at the end of the last ice age, which reached a plateau with peak Holocene temperatures about 7,000 years ago. This was followed by a long phase of cooling through to the Little Ice Age of the Northern Hemisphere, starting about 7 centuries ago. This trend should be continuing, ultimately driving the start of the next glacial interval. But the anthropogenic greenhouse gas emissions discussed earlier have resulted, commencing from the 1850s, a marked reversal in this trend towards warming temperatures, shown in the lower figure. The most marked increase has been a 1 degree global temperature rise since 1975, about a decade after the main upturn in CO2 increase. The current rate of rise of 0.02 degrees per year is almost an order of magnitude faster than average temperature rise at the Pleistocene-Holocene boundary, though not yet at the same scale. Recent work suggests that current temperatures now exceed Holocene peak, and the planet is the warmest it has been for 125,000 years, when sea levels were 5 to 9 meters higher than today, despite CO2 levels being more than 100 parts per million lower. So following several thousand years of near stable sea levels during the late Holocene, since about 1860 there has been an increase in global sea level of about 0.25 meters, at a rate that has been increasing since the 20th century, and is currently 3.7 millimeters per year during 2006 to 2018. The final type of signal I wish to discuss is how the biology of the planet is being modified during the Anthropocene. So as an example, this Virginia creeper, a native of eastern USA, lives happily alongside a red-hot poker which is native of South Africa, both occurring in an English garden. This association would not have been possible at any previous time in the geological past. Such global transfers of species is a distinctive feature of human management of biodiversity, in this case by enriching the diversity of plant species present through translocation. Such translocations of species represent a rapid and significant biostratigraphical change. One significant driver is the opening of global trade networks and transport of species in the ballast water of container ships between ports, leading to greater than 250 introduced species in places like the Mediterranean and San Francisco Bay in the Americas. In many cases, these introduced species can become dominant. For example, non-native organisms in San Francisco Bay typically account for 97% of the total number of organisms and 99% of the biomass. What may be the future scenario for the biosphere? Current extinction rates of species, which are shown here in black, are typically up to 2%, which is considerably higher rates than over the last million years. It is estimated since 1500 that 617 vertebrate species have become extinct, or extinct in the wild, or presumed extinct. It is often difficult for ecologists to establish the species have become truly extinct rather than exceedingly rare. And such uncertainties make the work of present-day paleontology doubly difficult. However, when one considers threatened species, such as those on the IUCN Red List, magnitudes are creeping towards the 75% threshold for global mass extinction. We're not there yet, but on current trends, it may take just 200 years or so, and this would represent the planet's sixth mass extinction over the last half a billion years. Even if the climate of the planet eventually, after hundreds or thousands of years, returns to something similar to the Holocene, and that is not certain, the fossil record of the Anthropocene will be fundamentally and permanently different, impoverished in diversity and abundance, extensively homogenized, and totally dominated by remains of humans and our domesticated species. At present, more significant than extinctions are precipitous falls in species populations. So these figures from the WWF Zoological Society of London Living Planet Index indicate a global decline of about 69% across more than 5,000 species in less than 50 years. This is even greater in Latin America and the Caribbean, where an average of 94% fall is recorded across more than 1,200 species. Natural processes of evolution are slow in comparison with the scale of the Anthropocene, so there are few new species that could mark the onset of the Anthropocene. But human forcing of biology in domesticated species can drive remarkably rapid change. For example, there's been more than a doubling in size of bones in domesticated chickens compared with the red jungle fowl, mostly since the mid-20th century, and an up to 5-fold increase in body mass. They're the same species, but the nature of the bones that are left as the geological evidence would appear to future geologists to represent a rapid evolution. And bear in mind, they are extremely common, with 66 billion slaughtered per year. That's 3 times the biomass of all wild birds. Next, I briefly wish to touch upon the existing work of the Anthropocene Working Group to formalise the Anthropocene. The standard protocol governed by the International Commission on Stratigraphy is to mark the base of the chronostratigraphic unit with something called a Global Boundary Stratitype Section and Point, or GSSP, commonly known as a golden spike. This is a reference point located in stratigraphic section, and there is a number of criteria required to choose the ultimate site. So it must contain a stratigraphic marker that defines the lower boundary and allows correlation globally. It must be defined by an observable change in the physical properties or physical content of the strata and should be datable. It must have adequate thickness to support global correlation. It must be continuous without any changes in facies. It should be unaffected by tectonic and sedimentary movements. It must be accessible to research and free to access, and should contain as many specific marker horizons or other attributes as possible, favorable for long distance correlation. Project funded by HKW, the House of World Cultures in Germany, which is their National Centre for the Presentation and Discussion of International Contemporary Arts, in collaboration with the AWG, started in 2020 to co-fund investigations at potential GSSP locations, with research led by each site for different institutes. The 12 sites came forward as potential candidates, these spanning 5 continents, though sadly none from South America. It's also sadly true that of the 79 GSSPs already defined throughout the geological column, none are located in South America. The sites occur within 8 distinct environments. There's one site in an anoxic marine basin, that's the Baltic Sea, 2 in estuary or coastal settings, that's San Francisco Bay and Beppu Bay in Japan, 2 are in corals, one's in the Gulf of Mexico and 1 off Australia, 3 are in lakes, that's Searsville in the USA, Crawford in Canada, and Xihailanguan in China. There's a peat in Poland, an ice sheet in the Antarctic Peninsula, a cave, Speleothem, from Ernesto Cave in Italy, and anthropogenic deposits in Vienna. Although we have to select just one site, which will be announced, which has been announced this week, looking at the 12 sites as a whole also contributes to our understanding of the Anthropocene. 12 sites, when viewing spheroidal carbonaceous particles, plutonium, radiocarbon, and stable nitrogen isotopes, can show broad ranges in onsets, which is the bottom of the line shown here, and peaks, which are at the top of the line. They may range in levels by many decades, but there are broad consistency in the level of rapid change at around 1950, particularly for the plutonium and spheroidal carbonaceous particle signals, shown as a black box and a black circle respectively. This in effect is an upturn of the great acceleration curve. It does show that global correlation of the base of the Anthropocene is achievable in widespread environments. So earlier this week, on Tuesday, we announced which of the 12 sites would be included in the Anthropocene Working Group proposal as the candidate GSSP site for the Anthropocene. And the winner was Crawford Lake, located 80 kilometers west of Toronto in Canada. The chronology is in part determined by distinct seasonal varves comprising dark organic laminae, including accumulations of plankton in the autumn and capped by pale calcite laminae each summer, with some distinctive thick pale laminae developing during the Dust Bowl in the 1930s and very thin calcite laminae above 1950. The initial interest in the site was that the core shows distinct phases of increased nutrient loads and plant remains from pre-European and European settlements that are specifically related to farming methods with an intervening 4 centuries interval where settlements were absent. The proposed base is taken at 1950 from the onset of the bomb peak in plutonium, but also seen by marked inflections in spheroidal carbonaceous particles, stable nitrogen isotopes, and biostratigraphic markers in microfossils. These include increased abundance of the algae Cyanura, notably sharp declines in planktonic diatoms such as Fragillaria, and a very clear loss of the diatom Lindavia michiganania around the 1950s, and rises in non-planktonic foraminifers. There's a brief increased abundance of the planktonic diatom Asterionella formosa, common in North American lakes, with preference to the conditions of increased reactive nitrogen from artificial fertilizers and fossil fuel burning. So in summary, over 11,000 years, strata show increasing but gradual human modification of landscapes, geochemical signals, and biodiversity. This is all consistent with the Holocene. But substantial and approximately globally synchronous changes to the Earth system intensified dramatically in the mid-20th century during the Great Acceleration. This is the preferred start of the Anthropocene. Many anthropogenic geochemical signals are short duration. Rapid detection has resulted in effective mitigation measures. Such spikes are useful markers of the mid-20th century onset of the Anthropocene. Other geochemical and climatic changes will prove of long duration, whereas biotic change is effectively permanent and will characterize the future expression of the Anthropocene. So I thank you.
Said that we are going to open to some comments and to some questions.
Okay. Yeah.
Okay. A gente tem diversos elogios, mas tem uma das perguntas mas quais parâmetros são atualmente usados para definir que se passou de uma época geológica para outra? Ou seja, e também tem algumas perguntas falando por que eles estão considerando como uma mudança de época. Então, quais são os parâmetros para se definir uma nova época?
Well, it's one of the tasks we had to face was that when Paul Crutzen had that original idea of the Anthropocene, he was an atmospheric chemist. So he was thinking about the atmosphere, and he was noticing that there were changes to things like the carbon dioxide and methane concentrations in the atmosphere, as preserved in glacial ice, that showed that things were changing from really the end of the 18th century. But we as geologists had to look at what record we could find in the sedimentary strata, in corals, as well as things like the ice record. And many of those early signals from the early 1800s and late 1700s are very localized. They're more Northern Hemisphere, more Europe focused. So what we were trying to do was find a level where there seemed to be a consistent global change. So it didn't matter whether you were in North America, South America, Europe, Asia, you would be seeing a constant change. So what we wanted to do is look at signals which had been distributed by the atmosphere in particular, because they're the ones that get spread more widely. And a clear thing is the bomb spike that comes from the detonations of nuclear weapons. And that starts in 1945, obviously, but really escalates in 1950. But that just represents a useful marker. It doesn't change the planet as such. So we then looked at things like the burning of fossil fuels and what that can change. So not only does it change carbon dioxide and methane concentrations, but it produces these spheroidal carbonaceous particles, these little fuel ash particles. But it also increases things like concentrations of mercury and other heavy metals as well, as part of burning coal. And then there's the change in agriculture and how there's so much more nitrogen in the environment from the production of these artificial nitrogen-based fertilizers. All of these things are getting distributed in the atmosphere, and so creating a global picture. Things like DDT, so these are pesticides that were invented in the 1950s and used widely for several decades. Things like lead in gasoline, that was being used in cars, and that created a very prominent signal from the 1950s through to about 2000. So it was looking at this pattern of many signals all happening at the same time, but then having to decide on one particular signal that represents that transition. So the plutonium was the one that represents that very rapid change.
E agora a gente tem uma outra pergunta. Essa pergunta é do Eduardo Guimarães. Eu acho que ele fez quando estava sendo mostrado aquele gráfico da questão do concreto e do alumínio, que ele pergunta qual seria a quantidade de rocha calcária que é usada para a produção de concreto. Eu não sei se o professor vai saber. E se esse valor é superior ao que se usa na agricultura.
I must say, I don't know that answer. I mean, what we did to work out the concrete production, because there's no production figures for concrete. So all you can do is go by the amount of cement that's produced, and then assume a certain ratio of the cement versus aggregate that you use to make concrete. So there's usually a fixed ratio of the two. And from that, you can then calculate how much concrete is produced per year. And the amazing thing was that we reckoned that half of all of the concrete ever produced has been in the last 20 years. So it's incredibly rapid. And we argue that it's probably the most voluminous artificial rock on the planet. But I don't have figures for how much is used for agricultural use. I mean, I don't know if that sort of production figure is available.
Gente, tem uma também do Daniel Nava. Existe alguma relação observável entre as atividades de vulcanismo, abalo sísmico e temperaturas oceânicas? E o Antropoceno, nas temperaturas oceânicas seriam El Niño, Laninha?
No, I think the understanding of this 1 degree centigrade increase globally is entirely the anthropogenic impacts of burning fossil fuels. But the interesting thing is the lag, I think, between the temperature rise and the increase in carbon dioxide in the atmosphere, which is what should be driving the change. That I mentioned that the big increase happened from 1975 onwards, and yet we were saying carbon dioxide concentrations increased very rapidly in the 1950s. And there's some debate as to why, if I don't know if it's possible to go back to slide 25. Is that possible? Yeah, so it's this bit from 1975 through to about 1940, around about then. You see it's flat. It's not increasing. It had started to rise from about 1850 onwards, slowly. By about 1930, it then flattens until 1975. And there's some debate as to what has caused that flattening. And it seems to be partly possibly related to a decadal scale cooling effect in the Atlantic, which is cyclical and in sort of part of a normal natural cyclicity. But the other possibility is that it's the amount of aerosols and particulates released by the burning of fossil fuels at that time at the Great Acceleration, in effect stopped some of the heat energy getting in to the Earth's surface. And so actually it suppressed temperatures for 30 to 40 years. And it's only the introduction of a number of clean air acts across the planet that then allowed the solar energy to get back in and also then be influenced by the increase in carbon dioxide. So climate is a very complex model to be using as a guide to understanding the Anthropocene. And in some respects, there is this time delay, which is why it's not a good marker for the onset of the Anthropocene.
Thank you very much. We are so glad to have you here. It's so important, this notice, even of the Ontario Lake. And now I will open for your last words, and then for Roberto last words too. Thank you. You can say.
It's been a great pleasure speaking to you again, and to everybody else who's had the chance to listen in today. I hope you found something of interest, and the topic is something that we all need to be thinking about, and as geologists helping to contribute to understanding it even further in the future. So please carry on the good work.
Da minha parte, eu vou ser bem breve, assim, eu gostei muito, me trouxe, me aclarou várias dúvidas, né? Me deu um norte em relação a pesquisas futuras, de como encarar certas coisas, né? A questão dos microplásticos, ela está aí, já está posta, ela hoje já é tema de submissões, de propostas, inclusive onde o SGB participa, né? Então já é alguma coisa que a gente tem que se preparar analiticamente e metodologicamente para dar conta, né? A mesma coisa, as questões isotópicas, elas são já de nosso conhecimento no SBG, né? A gente lida com isso, tem gente trabalhando com isso, então tudo que o professor falou nos afeta, né? E nos abre novos horizontes, sem falar nas questões estratigráficas em relação ao uso e ocupação do solo, né? O reflexo que isso pode ter para as pessoas lá do DGET, que estão trabalhando com mapeamento de risco, deslizamentos. Eu acho que tem coisas aí, interfaces muito interessantes, né? Do ponto de vista filosófico, como indivíduo, agora eu, Roberto, falando como Roberto e não como funcionário do Serviço Geológico do Brasil, são questões que me preocupam, né? Essa grande aceleração a partir de 1950 me preocupa como indivíduo, como cidadão, do ponto de vista ético, né? Me faz olhar para a minha cozinha, para a minha casa, no meu padrão de consumo, no que eu compro, de quem eu compro, o que eu uso, como eu uso, o que eu descarto, né? O que eu quero para as próximas gerações, para os meus filhos, para os meus netos, e o que eu posso fazer para provocar um decrescimento, né? Existem marcos filosóficos nas ciências sociais que falam e propõem um decrescimento gradativo, né? Esse decrescimento nada tem a ver com uma volta às cavernas, não. É simplesmente parar para pensar naquilo que a gente está consumindo, né? E ter escolhas como consumidores que somos, né? No sentido de buscar uma sustentabilidade em relação às coisas e não comprar tanto. Ninguém precisa muito, né? Então, para mim, escutar isso, né? Que é uma coisa que eu acredito quase como uma religião, escutar isso como um prognóstico geológico, acaba que fica muito redondinho isso, na minha compreensão filosófica, eu diria assim. Então, com isso, eu também encerro aqui. E, Patrícia, passe para vocês a última palavra, agradecendo muito ao Café Geológico e desejando longa vida ao Café Geológico.
Obrigada, Roberto. Thank you, professor Collins. Bom, eu agradeço, então, pela brilhante palestra e pela participação do nosso assessor de assuntos internacionais que tanto engrandeceram o Café Geológico.